Science Symposium last fall. And it's some work, again, these originated in Russia primarily. And what you see are similar pulse height spectra at the top for a case in which there's an average of 3.7 photons per pulse. Very nicely resolved. But what's astonishing is that you can still resolve the number of photons being counted out to an average here in this distribution of 96. So you can, in fact, do measurements with these remarkable devices that can tell you whether 95 photons hit the device or whether 96 hit the device, because you have that degree of resolution in the output. So it is a jump from analog readout using a photomultiplier to digital readout. Now this is not quite pure digital readout. You would need separate addressing for each cell. That hasn't been done yet, but I'm pretty confident some clever, innovative group is going to do that and make this entirely a digital readout of these devices. We heard yesterday again in the medical imaging section, one of the advantages of these devices is their immunity from the effects of external magnetic fields. And as the world of medical imaging transitions into combined modalities where you have both CT and PET, or PET and MRI, the MRI, of course, requires strong magnetic fields, and photomultiplier tubes become inoperable in that application. So attention certainly is being paid to these so-called silicon photomultiplier tubes in that context. They're still very small. That's the one major drawback. No more than a few millimeters on a side. There are certainly many groups, many companies quite interested in scaling up the size and the area to begin to compete with larger size photomultiplier tubes. Not there yet, but it's coming. I mentioned one of the driving forces here is the appearance of applications where there are a greater and greater number of parallel readout lines. And here's an illustration, again, of the group that's pushing the technology the hardest. That's from the world of high-energy particle physics. And this is now fairly old plot back to 2004 by Paul O'Connor, who simply plotted the density of the readout in terms of pixels per square centimeter, or how many readout lines are there per square centimeter of the sensor, versus the year. And notice this is a logarithmic scale, so this is a very abrupt exponential rise. This is just a consequence, to some degree, of Moore's law that anyone working in integrated circuits is quite familiar with. The capacity per unit area on a chip grows and doubles something like once every 18 months. So this is simply exploiting the capability of microcircuitry that is growing up certainly in many other fields, consumer electronics and elsewhere, that helps allow this kind of degree of sophistication. Well, I'd like to illustrate that with the work that's going on in our department by my colleague Zhang He and his group. Again, I mentioned Misha Rodriguez, who's one of the members of that group, although he's in the Brazilian Navy here. He is pursuing his doctorate with Professor He on our campus on occasional visits. Well, this, if anyone was at, those of you who were at Misha's presentation, he showed a device that's a semiconductor detector operated at room temperature. This is intended to do gamma ray measurements. And the standard semiconductor material for gamma ray measurements is germanium. Germanium has a narrow band gap, 0.7 eV, and so it always needs cooling, traditionally using liquid nitrogen. And that's a great operational inconvenience, as we all know. Semiconductors with wider band gap permit room temperature operation, and there are several examples that I'll show. This particular one is with what's called CZT, or cadmium zinc telluride. It's a blend of zinc telluride and cadmium telluride. And it can be operated at room temperature. And the object in this case is going to be not only to measure the energy of gamma rays coming in, but also to record where they interact spatially in the device in 3 dimensions. Now that's not easy to do in a standard scintillator, for example. You lose the spatial information because the light spreads isotropically from the point of origin, so it is sort of hopelessly blurred by the time it reaches the surface of the scintillator. Not so in a semiconductor detector, where the charges, when they are formed, move very closely with the electric field lines. And so, if the field lines, in this case, we're running vertically, then the electrons that are formed here, ionization electrons, would tend to drift directly downward to the bottom surface. That allows then a 2-dimensional readout if one of these surfaces is pixelated. That is, it's made up of a fine checkerboard of anode pixels, each one of which is electrically independent, and each one of which is now connected to its own readout chain. Hence, here's where ASICs come into the picture. You could not seriously think about connecting 121 separate preamplifiers here in 10 years ago, where you have discrete components. But it is certainly very conceivable to now make this device with an ASIC whose readout pitch is matched to that of this checkerboard pattern. So that's the approach. And by simply now noting which one of these pixels lights up, which one triggers a pulse in its readout channel, you can then get a 2-dimensional XY piece of information. Now the 3rd dimension, the depth below that surface, can be obtained a couple ways. One of them is to do the cathode to anode ratio. That is, if you read out not only one of these pixel anodes, but you also read out the opposite planar electrode, the cathode. It turns out the ratio of those 2 signals is proportional to the distance that the electron travels. Now I'm talking almost exclusively about the electron motion here. Neglecting the holes, of course, electrons and holes are formed in equal number by the radiation, but the holes, in contrast with germanium, where they move quite nicely, the holes in these compound semiconductors, like CZT, move very slowly. And in fact, they are almost always trapped very close to their point of origin, and so they, to first order, contribute nothing to the output pulse. So these are electron-only devices. That proves to be necessary because of the poor hole transport in many of these compound semiconductor materials. There's a second way to get depth, and that's by timing. I'm not going to go into the details here, but you can imagine the drift time, the time it takes the charges to move from their point of origin to the collecting anode, is directly proportional to the distance that...
Perdeu 29, que a cada 10 minutos ela desliga.
Another thing that can be accomplished by the 3-dimensional readout is something I mentioned briefly earlier. These materials, CZT, and I'll show a couple other examples later of room temperature material, these materials are far from perfect. In fact, they do a great deal of charge trapping. This is not something that generally is of significance